In the previous video, we were able to run a containerized version of our application on Amazon Elastic Container Service. If you go back to our console, we created a cluster called the ECS Fargate cluster to which we attached this specific task. This task made use of the Docker container. The Elastic Container Service exposed our application to the outside world on port number 8501. After the application was exposed, we were able to access its UI and send a news article for it to summarize. Behind the scenes, at runtime, when we sent this article, the application was able to access the secrets manager and there's our OpenAI's API key, inject that API key into the application's prediction logic, and thus using LangChain, that is LangChain's summary chain, it was able to invoke the GPT model on OpenAI, and whatever text we have passed, it was able to summarize that and return it back to the user as summary, that is a response. But that is all about testing an application. We have yet more work to do to build a scalable service, which is exactly what we will do now. That is, we will now add an application load balancer to our service. But before we add this load balancer, we need to first understand the difference between horizontal and vertical scaling. So in lieu of what we have done so far, we have a text summarization app, which receives text from the user and it sends a response back as a summary of that text. So the text summarization app which I'm talking about here is the app.py file as well as the requirements.txt file. This text summarization app sits inside a Docker container. That is, if you guys remember, we made a Docker container image and we pushed onto Elastic Container Registry, that is ECR. When we finally made a cluster on Elastic Container Service, we chose a certain configuration. And that configuration was 1 CPU and 3 GB RAM. So what really happens is this Docker container image is then copied over to an EC2 machine. That is an EC2 machine with 1 CPU and 3 GB RAM. That is how behind the scenes it works. You build a Docker container image and then it gets copied over to an EC2 machine. Now in production systems, there are certain system level metrics which are monitored by site reliability engineers or let's say by DevOps engineers. The role and the responsibilities vary. We're not concerned about that. So the system level metrics are, let's say, CPU usage. We have 1 CPU. How much of that CPU is being used? That is something which will be monitored in terms of a dashboard. How much of the 3 GB RAM is actually being utilized based on the number of text data which we are receiving, and how many requests per second is our system actually processing. And there are a couple of other metrics as well. To simplify, let's say we just focus on the number of requests per second our system is receiving. Let's say we design this application with the current setting, that is 1 CPU and with 3 GB RAM, our system is able to handle a max of 70 requests per second. But in a given instance, let's say the number of requests which we get was another 100. That is a total of 100 requests. So to summarize, our system with 1 CPU and 3 GB of RAM, that is with this current machine, our application is able to handle 70 requests. But in a given second, we actually get 100 requests. What exactly will we do with those additional 30 requests? That becomes a question to be solved. So that now becomes an engineering challenge. We could either take those 30 requests or discard them, but user number, let's say for each user sends one request. So user number 70 send the 70th request, but user number 71 to 100 would then be, let's say get a response back from the server that your text could not be processed. Something like that. A message which basically discards their provided input. But that is not what we want, because we want the application to be exposed or be accessible by everyone. There's another solution, which is basically we could queue their responses, that is put them in a queue. So after we are done processing the 70th request, then we start processing the 71st request. all the way to the 100th request. So the 71st request gets processed after the 70th request. So naturally, it will have to wait some time. That is, from request number 1 to 70, all these requests would take, let's say, time t. 71st request would take, let's say, time 1 second. So that is t plus 1. And for 100, it would naturally take some more time. So in all, the total time the application, these requests wait in the queue and processed and then get sent over to the user as a summary now become higher. So the overall inference latency becomes higher. So this is again not a viable solution. So that is why we have to scale our application. That is, if we get more number of requests, then that is permissible by our application to be processed in a given second. We can't just let the users wait. Otherwise, they will find our application to be non-useful and then they'll rather go to a competitor, which basically provides a similar service. So that is where the scaling part of system design come into play. So there are two options which we have at this point. We could either choose a bigger machine. That is, we could have X number of CPUs in our EC2 machine, or we could have Y with Y GB of RAM, where X is more than 1 and Y is more than 3. Remember, like we chose the bare minimum. We choose 1 CPU with 3 GB of RAM. We could choose, let's say, 10 CPUs with 80 GB of RAM. So as we get more number of requests, our CPU and RAM or memory usage power is solved. If it gets consumed a lot, let's say 90% of this one CPU was being used, but with 10 CPUs, we can actually process much more number of requests. And let's say out of this 3 GB, 2.9 GB was being utilized. And for these additional 30 requests, since we don't have the memory capacity, 80 GB of RAM can actually handle 100 and actually much more requests than that. But if we use this approach, that is with 10 CPUs and with, let's say, 80 GB of RAM, this machine would always be running. And in scenarios or in situations where we don't get that high volume of requests per second, we will still be charged. So that is why vertical scaling is even though it's a solution, it's not a very preferable solution, because we want to be very dynamic about how much money do we actually pay out for scaling our application. So a better solution is horizontal scaling. And the way it works is that whatever application you had here, that is your Docker container, your text summarization app sitting inside a Docker container, and that Docker container is sitting inside your base EC2 machine, which was 1 CPU with 3 GB RAM. How horizontal scaling works is you just take this entire system, that is EC2 machine, with the Docker container holding your app, and you make replicas of that. So let's say we have 3 replicas. Each replica is a EC2 machine with 1 CPU and 3 GB of RAM. And now you have 3 machines, each one holding your application, that is your containerized application. In front of these EC2 machines, we add a load balancer. Now, load balancer is basically attached to each of these EC2 machines. And then the load balancer's IP address is then exposed to the user. At runtime, when a user sends a request, the load balancer would basically check like which particular machine has a tendency or maybe a capacity to process those requests. Let's say this particular machine was utilized completely. This machine was also utilized completely, but this machine on the first machine on the left had, let's say, its usability is only 30%. So the request which the user sends would be sent over to the first machine. This is done by an algorithm which the load balancer uses, which could be, let's say, round robin. It could basically send the request to the first machine, then the next request to this machine, or it could be random, or it could be based on the load of the machine. So more information could be found online. I'll also share articles around this topic, like how the load balancer actually distribute those requests. But our focus is to design the infrastructure. And then once you design that, then I would recommend that you read the theory. So then the public IP gets exposed to the user. And then finally, since we have replicas of our particular EC2 machine, multiple requests could be handled at the same time without actually adding them to the queue. Another advantage of this approach is that when the number of requests become lesser, then this copy of our application and this copy could be removed safely without actually like basically breaking down the entire system. And as the workload increases, that as we get more number of requests, more number of copies could be added. You can in fact add another load balancer here. So another usage of load balancer is it also monitors the health of your system. That is, if let's say for some reason this Docker container breaks, then we already have 2 more Docker containers. And given the amount of workload we have at that time, it could basically add another EC2 machine with a copy of a Docker container. So those are some of the advantages. You will find a detailed explanation of the usage of a load balancer and how horizontal scaling is preferred over vertical scaling in the PDF for this session. So in the next section, I'll be teaching you how to add this particular load balancer to your application. And to do that, we first need to tear down the current architecture which we have set. That is, we'll be closing down this cluster and the task. And to do that, all you need to do is go to your Elastic Container service page and just click on the task. After you click on the task, just select this option and under actions, click on deregister and just go ahead and click this. So the task has been deregistered. Now let's go back to our cluster. Just click on the cluster, click on tasks, click on this particular task, and under stop, click on stop all. And it will ask for a confirmation. Just go ahead and click on stop. So the task has been stopped successfully. After that, just click on delete cluster. So it would want you to type out the name of the cluster just as a fail-safe mechanism to basically seek your confirmation. So just type delete followed by the name of the cluster and click on delete. So it is in the process of deleting the cluster. After deleting the cluster, we won't be able to see any more clusters on under the cluster section and no tasks under the task section. In the next video, I'll teach you how to create, like we will basically be creating a new cluster altogether. We'll be creating a task, but we'll be creating a service from that task rather than just running the task. And then actually we'll add a load balancer to it so as to scale our application. And finally, we'll be making use of auto scaling groups offered by AWS so that our application couldn't be scaled up or scaled down based on how much workload or how many requests per second are we having in a given instance. So I'll see you in the next video now.